Okay, yeah, and the question, of course, is how to derive such canonical representations for complex objects, how to derive feature vectors for complex objects. And there are basically two ways to do that. The first, more traditional way to do it is to do it by hand. Yeah? That gives us handcrafted features. So we have also terms like similarity modeling or similarity models, feature transformations. People use these terms to denote that the features are somehow handcrafted. Yeah. So as I said before, the traditional way to do it, yeah, for a long time it always works somehow. Yeah. The question, the procedure is as follows: we define features manually. We'll see some examples on the next slide, and then transform the raw data into these manually defined features. Yeah. So we extract features from the complex data. The downside, of course, is it requires a lot of engineering and a lot of domain knowledge, because typically we as computer scientists have no idea about the business, about the application. So the question is how to come up with good features for a given application. Yeah. So I think I already mentioned that last week. So in the computer vision domain, for example, for images, you can have 20,000 different feature transformations. So the whole image community, computer vision community, was in the past 30 years more or less about how to derive different feature representations for different applications. Yeah. So for example, if you are interested in the color scheme of an image, then you should derive some color features. Yeah. Features that describe the color of your images. If you are interested in objects within the images, then of course you need to derive features that somehow model or describe those objects in the images. Yeah. So that's what you just said, that there is, even for one specific type of data, there are hundreds or even hundreds of thousands of different feature transformations. Yeah, so it requires a lot of engineering. It's very domain specific and application specific. But in principle, it always works as long as you have someone that tells you those and those features are the most important ones. Try to derive it. Yeah, it's just an engineering task in that case, just one. Yeah, but anyway, so in principle it always works, but of course, it can be cumbersome. Yeah, special cases that you got to know already are so-called, or got to know if you attended KDM, are kernels, which are specific similarity models, which use a kind of implicit representation. So just if you recall, kernels in the linear models, SVMs and stuff like that, when Matthias Renz talked about support vector machines, he probably also talked about kernels, which uses an implicit similarity model, actually. Yeah? So just that you know, those are basically, kernels are basically similarity models. And now the second way to do it is feature learning, also called representation learning. That is the new way to do it, the fancy, the cool stuff, because that's deep learning actually. Wow, deep learning is the cool stuff. But of course, not always. It's not the one-fits-all solution, but anyway. So let's have a closer look. What do? You learn the representation typically by applying some learning techniques, and this is typically deep learning. So representation learning more or less is the same like or equals deep learning. Yeah? So you apply some deep neural network on that. It usually works pretty good for unstructured data. Yeah. So think about where does it really work good? Images, yeah, because an image is a set of pixels, and that is first of all completely unstructured, yeah, and each pixel on its own has, so if you're interested about in the information about what kind of object is in the image, one specific pixel has no clear relationship to what is actually on that image, but the combination of different pixels give you different objects in the images. And deep learning, neural network deep learning approaches are very good in somehow finding those relationships between different pixels, different features in that case. So usually works pretty good for unstructured data. sounds really, really appealing in a general way. It is actually appealing, but there are a lot of pitfalls. Very often it's not really working for structured data, yeah. And also for unstructured data, you typically need a lot of training data, a lot of data to adjust or to learn those deep learning models, as you probably know. So it is, as I said before, not the one-fits-all solution. So both solutions are actually somehow orthogonal, yeah. And you, as a kind of data miner, a data scientist or machine learner or whatever, should be clear about those two different ways to do it, yeah. So you have your raw data, you should come up with some patterns, and you have to do pre-processing typically in order to get, yeah, feature vectors or some other representation by representation learning algorithms like deep learning models or stuff like that. Yeah, so always keep those two ways in mind, because in a specific situation, it's better to use handcrafted features, or you can only use handcrafted features. In other situations, it's possible to do feature learning. That you probably try to do feature learning in that case. Yeah? So always keep these two things into account, and we will basically, as I told you also last week, basically talk about handcrafted features and the traditional way to do it in this lecture. And there is the other lecture about neural networks and deep learning, which will talk about this part here. And we also talk about this part here in the lecture of big data management and analytics a little bit more next year, next semester, so to say. Yeah. Okay. But once again, they are not competing, but they are somehow orthogonal, these two ways to do it. So how can we do the manual way? How can we do the traditional way? The feature transformation, well, the general concept is, as said before, we extract characteristic features from each object. Usually these characteristic features are numeric features. So each object is represented as a high-dimensional feature vector. So in case of numeric features, we are talking about points. Yeah? And characteristic features means that, so if we really extract characteristic features, that means that similar vectors, similar feature vectors, indicate similar objects. But that is only true, of course, if the features are characteristic, yeah, for our application. So that's why it's very important to actually grasp characteristic features. So here you see the general way to do it. Yeah, so we have complex data like time series, 3D structures, 2D images or 2D structures, images, again, images or sequences of images, whatever. And you can try to extract features from all that different stuff, yeah, and bring each of these objects into a specific canonical representation. Yeah? So if you have a set of 3D structures, you can try to model these 3D structures in terms of a feature space. And each 3D structure would be then represented as a point in this multidimensional feature space. That is the key idea. And here are some examples that you probably already know. So text, what can be done with text? Well, you can transform text into so-called TF-IDF vectors. So they are basically term frequency vectors. So TF is term frequency. So you just simply count for each possibly occurring term the frequency of this term in a given document. Yeah? So then you can transform each document of a collection of documents into a high-dimensional feature space. So that is the so-called bags of words approach. Yeah? For images, there are a lot of handcrafted feature transformations available, like color histograms, if you are interested in more in the color gradient, for example. SIFT are more high-level features that are for object recognition and stuff like that. For graphs, for example, you can kind of come up with the so-called shortest path kernel, where you simply do some shortest path computations between nodes and store that as features in your representation. Categorical data can also be represented as feature vectors by a so-called one-hot encoding. So TF-IDF, graphs very often, also categorical, so one-hot encoding, that leads typically to very, very high-dimensional feature vectors. If you attended big data management and analytics, we talked about sparse data. That is exactly sparse data, because the problem here is that each feature in a one-hot encoding, or here in the text, basically stands for a specific concept. Yeah, so in that case, a specific term here for text, or for the categorical data for a specific category, yeah, for a specific value, and we actually encode here the existence or non-existence of these concepts. Yeah, and typically you have a lot of concepts. So take these term frequency vectors. So how many terms do we have in a dictionary? Yeah? Just look in the dictionary of English words. Of course, you do a lot of things like removing stop words, which are irrelevant, like, I don't know, he, she, is, or I, and stuff like that. And of course, you do stemming, like, using the ground form, like buy, to buy, instead of bought and buying and stuff like that. Yeah, so you reduce the number of available terms, so to say, in your dictionary, but still there are typically several hundreds, even hundreds of thousands features. So the feature vectors are 100, 200,000 dimensional, yeah, and a lot of those features, a lot of those terms will not be present in a given document. So there will be a lot of zeros in these feature vectors, which we call sparse representation in that case. Yeah? And the same is true typically for categorical data. Also for graph data, if you think about adjacency matrices for graph data and stuff like that. Yeah. So, but they are that is a different kind of story and different kind of problem. But typically, feature transformations end up in having quite high dimensional feature representations in practice nowadays. Actually, that was a little bit different some years ago, but typically you try to model a lot of semantically important things, and then you need to come up with a lot of features, meaning that you have a lot of dimensions in your feature vectors.